So sad. What's this, 2-7? Reasons to have inverse functions. It's always nice to know why you're going to do what we're going to do. So here's the reasoning behind it. If we have this equation, and I ask you to solve it, what is the first step?
Subtract 3 on the other side.
Oh, we're just going to move it for the fun of it? How do you move it?
Negative 3 on. Subtract 3 from both sides.
Subtract 3 from both sides. So you go minus 3 here, minus 3 here. Why do we choose minus 3?
Because you can't do it 2 yet. It's with the variable.
I know, but why minus 3?
Because it has to equal 0.
We want it to equal 0. So what are these two things called?
Invert.
Specifically, additive inverses. So that allows you to go 2x plus 0 is just plain old 2x is equal to 4. All right. Get rid of the word multiplication. I'm sorry, division. How do you solve for this x?
You said what?
Get rid of the word division. How would you solve for x?
He said, don't say division.
Yeah, don't say division.
Don't say divide. So multiply by. I know, a half. So you multiply both sides by a half. I mean, multiplying by a half is the same thing as dividing by 2. What are these two called? Take a guess.
Multiplication inverse.
Yeah, but there's a fancier word. Multiplicative. Multiplicative. I'm not going to write it all out. Multiplicative inverses. Multiplicative inverses bring you back to the multiplicative identity, which is 1. 1 times x is x. A half of 4 is 2, and we're down to our solution. So even back then, you were using inverses to solve equations. You were using inverses to solve equations. So, for instance, this equation you should be able to solve. Oh, I'll give you a hint then. You don't think you can solve it. Ready?
4.
Box plus 2 equals 5. Did you use any algebra to come up with 3? No, you kind of mentally went, oh, what plus what is equal to 5? So what power would I have to raise 2 to get to 16? So right off the bat, we can say x is equal to 4. 0 algebra. It's the same process as box plus 2 equals 5. You're 2 to the second, 2 to the third, 2 to the fourth, and you kind of get the answer. All right. The problem comes when you have 2 to the x equals 25. What power do I raise 2 to get to 25? And your answer is? You can't accurately do this unless we have something else. What we're going to eventually learn last chapter, chapter 4, is the inverse function of 2 to the x. So we can wipe it out and get x equals by itself. You don't get the x by itself. Problem is x is up high and you don't know how to deal with that. So eventually we're going to come back to this idea of inverse functions and actually solve this equation and actually learn what x is equal to. The best we can do right now is, let's see, x to the 4th is 16, x to the 5th is 32, right? Oh, I'm sorry, not x to the 2 to the 4th is 16, 2 to the 5th is 32. So this answer has to lie someplace between 4 and 5. That's another fancy theorem in mathematics that we're going to deal with in the next chapter, called the intermediate value theorem. So we need these inverse functions to undo things that we don't know how to undo. I mean, you learned about inverse functions in 4th grade, but you really never applied them. So I'm going to teach you the inverse functions first, and then we're going to apply them. The whole point is to undo what was done. So, inverse functions undo what a function does. If we kind of consider 2x plus 3 as our function, well, 2x plus 3 takes a number, multiplies it by 2, and adds 3 to it. To undo it, you subtract 3, you divide by 2, and you get back to your answer. All right, so what if we have a function that looks like this? The way you need to look at it coordinate-wise is kind of individually. This point represents f evaluated at -2 is equal to 1. Kind of going backwards with our function notation. This one represents f of 0 is equal to 3. We're back to whisper mode, are we? Come on, you're going to have a whole week off. You can be as loud as you want today. Over here, you're going to get f of 2 is equal to 5. All right. So the f function is taking -2 and bringing it to 1, taking 0, bringing it to 3, taking 2 and bringing it to 5. So what would f inverse do? Now, f's inverse, we're going to write this way. That is not f raised to the -1 power, because Frank cannot be raised to a -1 power, because Frank is not a number, he's a name. So that is read f's inverse, or the inverse of f. So when I look for f's inverse, all I wanted to do is to go backwards. Where f took -2 and brought it to 1, we want f inverse to take 1 and bring it back to -2. So the first point will be 1, -2. All right? This one was 0 to 3. This point's going to be backwards. 3, 0. And the next one would, instead of 2, 5, would be 5, 2. And the green stuff is exactly what f inverse is all about. And this is how it would work. You would take f of, let's say, -2. We know what its answer is, right? Okay. If I compose that with f inverse, watch what happens. What's f of -2? It's 1, right? So then this becomes f inverse of 1. What's f inverse of 1? Back to -2. So basically, what happens to these two when they run into each other? There's -2 at the very end, and there's -2 buried inside here. What happens when these run into each other? They kind of go, don't say the word cancel, I say the word poof. They go poof, and you're left with -2. So one of the properties in inverse functions is this. If f inverse is composed with f, and they're defined over all the real numbers or the complete domain, then they kind of go poof, and you're left with the inside. So f inverse composed with f of x is going to equal x. Number 2, if you reverse the composition, now do you remember us reversing the composition last class? I said, are they going to be equal? And I said most of the time they're not going to be, and it's a special case when they are. Well, this is the special case. If I take f and compose it with f inverse backwards, it's also going to equal x. So this is really important about inverse functions. If you have inverse functions, that's the most powerful property going. That they cancel each other out, and you're left with the domain. You're just left with the domain. Those are the special case of composition. All right, so next question. Are all functions invertible? And what this word means is have an inverse. Are all functions, any function that you can think of, do they all have inverse functions associated with them? Are they invertible? You'd think they should. And the answer is, we'll find out in a second. So let's take G. G looks like this. -2, 1, 0, 4, and 2, 1. Is that a function?
No.
Why not?
A Y? Oh wait, no, it's supposed to be.
The x's can't repeat, y's can be exactly the same. So this is a function, right? All right, let's set up G's inverse. G inverse would look like this then. 1, 2, 4, 0, 1, 2. If you haven't figured it out yet, an inverse function just takes a domain and range and switches them. That's literally the entire section. If you ever are in doubt, take the domain and range and switch them. Is the green one, G inverse, a function?
No.
And the answer is no. So there's a problem. In this case, G inverse does not exist because these 2 points force this thing to be not a function. You cannot have the same x value going to 2 different y values. That breaks the law of what a function is. All right, so how do I determine what kind of functions are invertible and what kind of functions aren't invertible? Graphically, simplistic, very simple. 2 pictures. One is an invertible function, the other one is not invertible. Out of those 2 functions, which one do you think has an inverse? A or B? Or do both of them? Or do neither of them? Play the devil's advocate. Both have an inverse? The answer is nope. So which one definitely has an inverse? A definitely does not have an inverse. Now think about this. When we're dealing with the points, G by itself was a function. It was perfectly fine. It's when we flipped it that it became not a function. Well, what caused it not to be a function in G when we inverted it? The y value is repeated. So how do we determine in a graph if x values repeat? What test? Vertical line test. If you take the domain and range and switch it, the vertical line becomes?
What?
Okay, if you have a vertical line and you switch the domain and range, the vertical line becomes what? Horizontal. It flips because x becomes y and y becomes x.
Oh,
So, what?
yeah. I said, oh yeah.
Oh, I thought you said I don't get it. So the test that we're going to perform for one, if a function is invertible, is what's called the horizontal line test. That function is not invertible because that horizontal line is hitting it at 3 different points. Makeup points, -4, 2, -1, 2, 5, 2. If I take each one of these coordinates and flip them around, it becomes 2 something, 2 something, 2 something, and they're all different somethings. Therefore, it cannot be a function. Therefore, that graph is not invertible. It does not have an inverse. But if I look at this graph over here, and I pass a horizontal line through each one of its points, it's only going to hit the graph once. This graph is called 1, 2, 1, and it is invertible. There's one other little feature to that second graph. On what interval is that graph increasing? On what interval is that graph increasing? Increasing? Increasing.
It's like a negative slope to me.
It looks like a negative slope to me. It's never increasing. This graph is always decreasing. Look, if you go left or right, the second graph is always going down forever and ever and ever. So another feature to 1 of 1 is either A, always increasing, or B, always decreasing. It can't do both. Go back to that increasing and decreasing section. That might be on the quiz today. Well, it's definitely on the test.
You stopped my ABS.
Alright. So, definition time. The definition of a one-to-one function is almost identical to the definition of a function, except for one word. For every domain, there is, this is where it gets a little different. Now, the definition of function says for every domain there's exactly one range. This one goes for every domain there is a unique range. Now, when you say the word unique, it's one and only. One and only. If everybody had a unique height, everybody in this room would be different heights, which more than likely is true, but it's really hard to find someone exactly the same height. Okay, so another way of putting this. F, and this is actually important, F is one-to-one if and only if when f of A is equal to f of B, implies A is equal to B. Now, implications are really important. If the left-hand side is true, the right-hand side has to be true. So if f is a one-to-one function, and I know that f of A or f of 2 is equal to f of 3, then I know for sure that 2 and 3 must be equal, the same. So it forces the same point right on top of one another. 2 and 3 is probably a bad example because you're thinking of it as separate. This says they have to be the same point. So this statement right here is saying you're only talking about one single point on the graph rather than two. So if this is true, then f is definitely one-to-one, and if f is one-to-one, then this must be true. Okay. So horizontal line test if you have a graph. This piece right here if you have a function. That's how you would prove something is one-to-one invertible. For instance, for example, let's use this to prove something about this function. Is it one-to-one? So how do I use that little box to prove that that is either A, one-to-one, or B, not one-to-one? Use it directly. Assume that there is such a place as f of A is equal to f of B. Alright. Trick question of the day. I don't know what happens with students and their brains when I ask this next question, but their brains will usually just fall out and they forget everything. What's f of A equal to? Just 3? What is it?
3x squared?
Nope.
3x?
Like I said, brains just fell out. I could ask this any other place in the course and you'll all get it. I ask it here and, oh, well, there's that f of B though. Who cares about the f of B? What's f of A equal to?
Is it 3x squared minus 4?
What is it?
3x squared minus
3x squared? No.
Just X?
No. Why?
Why?
Why not? I'm going to be stubborn on this point. What's f of a equal to?
A squared.
No.
A.
Is equal to F.
What is it?
A.
No. F of x is equal to 3x squared minus 4. What's f of a equal to?
F of B.
Oh, I swear to God. I don't care about the f of b.
What, 3a squared minus 4?
What is it?
3a squared minus 4.
Thank you. 3a squared minus 4. Like I said, brains fell out. What does this tell you to do? It tells you to take x and replace it with a. All right. What's f of b equal to? What's
3b
f of
squared minus 4?
3b squared minus 4? Awesome. Do you see how silly that was now? Yeah. Okay. Generally, you can solve for either a or b, but most people choose a. Solve for a, what would you do first? How would you solve for a?
Add 4.
Add 4 to both sides. You get 3a squared equals 3b squared. How do you solve for a?
You want us to multiply or divide?
You could say the word divide.
Oh, divide.
Divide both sides by 3 and you get a squared equals b squared. Square root both sides and you get a equals
B.
My patience is starting. Oh, thank you. Plus or minus b. Because if you square root both sides of an equation, you have to tag in plus or minus to account for the positive root and the negative root. See, a could have been negative 3 over here, and b could have been positive 3 over here. If you square them, it's 9 equals 9. But a does not equal b. So this gives us two possibilities. A is equal to b, or a is equal to negative b. Is this a one-to-one function? Now remember, if f of a is equal to f of b, it implies directly that a has to equal b. Sure, it equals b over here, but it also equals something else. So is this thing one-to-one? The answer is no, not one-to-one. When you go through that work, your last step should just say a equals b, and you're done. Oh, by the way, the graph of this thing looks like this. What test does it fail? Horizontal line test. Definitely not one-to-one function. Not invertible over the entire domain. Not invertible over the entire domain. Can I make this invertible? Yeah. Easily. Actually, simplistically. Choose numbers that are always positive. If I choose numbers that are always positive, this will never happen. And we'll get a equals b. But that's called a restrictive domain, and we're not talking about that yet. But it is possible. How about this function? Just leave it alone. 3x cubed. Is this function one-to-one? See if our brains are warmed up yet. So if you're going to try to prove that this is one-to-one, you assume that g of a is equal to g of b for some numbers a and b. Whether they're the same or not is irrelevant. So what's g of a equal to? 5 minus 3a cubed equals 5 minus 3b cubed. The essence of what it means to be a function. All right, solve for a. Subtract 5. So you get negative 3a cubed equals negative 3b cubed. Fell asleep there for a second. Not yet.
Oh, divide 3.
Divide by negative 3, and you get a cubed equals b cubed. Now if you cube root it, I can write A
Equals B.
equals B. Because cube roots don't get the plus or minus, they just become whatever there are. So is this function one-to-one?
Yes.
Yes. One-to-one, invertible. In other words, G inverse exists. So what's the next question I'm going to ask?
Where's Waldo?
No, not in this room. Well, if G inverse exists, what is it? Right? Don't you think that? I think like that. Someone tells me a piece of the puzzle, I want to know what the other piece is. So, next part. How do you find the inverse? So I can work with it. Alright, steps. Usually in math, if you have steps, you can at least follow them for the first few times, figure out what the heck you're doing. So step number one, not so obvious, change f of x back to what it used to be. It used to be y. Remember when we started this, it was y equals something, and then we changed y into Frank and George and all that fun stuff. Here we want to go back to the essence of what the range is, which is just y. 2. How should I write this? Replace x with y and y with x. In other words, wherever you see an x, replace it with a y. Wherever you see a y, which is only one, so I hope, otherwise it wouldn't be a function, generally, replace it with an x. All right. At this point, once you replace the x's and the y's or switch them, you're talking about the inverse function. So right here, we're talking about the inverse. Actually, in some math programs, if you write this, that's the inverse function of y. Because you just took x and replaced it with y. So f of y must represent x. So you just did the domain range split. So some programs just understand that. We have to go a little further. 3. Solve for y. Sometimes easier said than done. Sometimes it's really simplistic, sometimes it's a pain in the butt. 4, everybody forgets this one. Replace y with the inverse notation, f inverse of x. That's it. That's all there is to it, to find an inverse function. Generally. So, for example, we know that g of x equals 5 minus 3x cubed is invertible. It's a one-to-one function. So I should be able to find its inverse. So let's go through the process. So here's g of x equals this mess. And step number 1 says change the function notation back into y. So g of x becomes y. So you get y equals 5 minus 3x cubed. Okay. Second step, take the x's and y's and flip-flop them. Basically, you're taking the domain and range and switching them. So wherever you see a y, replace it with x. Wherever you see x, replace it with y. Don't change anything else though. Leave all the powers and square roots and fractions wherever they were. Step 3 says solve for y. So how would you solve for y? Most people would subtract 5. What would I do? You don't think I would? I would add the 3y's cubed to the other side. Why? Because it makes it positive. But we'll subtract 5. X minus 5 is equal to negative 3y cubed, because most of you would do that stuff. But I can see a few steps ahead and I know what trouble's going to fall into play. Then how do you solve for y? Why? Stare at it. And it just gets weird, right? Divide by negative 3. Divide by negative 3. So I'm going to put the y cubed on this side is equal to, what would you write on the other side? Would you leave it like that? X minus 5 over negative 3? Doesn't sound right. So what trick can I play? Instead of leaving the negative in the bottom, put it in the top. If you put it in the top, distribute it. What's the top become then? Also known as 5 minus x over positive 3. If you commute over subtraction, it changes signs. Commute over subtraction. All right, last step. Well, not the last step. Last step for solving for y.
Cube root.
Cube root it. So you get y is equal to the cube root of 5 minus x divided by 3. Now the last step. Step 4 that everybody forgets. Replace y with the function inverse notation. In this case, what did we start with? We start with g of x. So over here we should write g inverse of x is equal to the cube root of 5 minus x over 3. And there's your inverse function. Yeah? You don't like that one? Let me show you what you can do with it. At least I think this will work. I've never tried this before, so it might blow up in my face. But you never know. You'd love to see something blow up in my face, right? Make a huge mistake. No? What? I'll make a huge mistake. Alright, so g of x is equal to 5 minus 3x cubed, right? Yeah. And g inverse of x is equal to the cube root of 5 minus x over 3. Yeah, okay. So let's say, just for fun, I had this equation. And I said, solve for x, but not algebraically. I'm going to do it fancy, weird. So what I'm going to do is, this side is g of x, right? This side? That's literally just g of x. So this is saying g of x is equal to 2. I want to show you what functions can do different than just regular old algebra. So if this says g of x is equal to 2, what gets rid of g? Because I want to get x by itself. Take a guess. That thing. G inverse. Remember, if g inverse and g run into each other, they go poof when they're composed with one another. So what I'm going to do is, I'm going to compose both sides, or evaluate both sides, at g inverse. Ooh, I wrote that one bad, but you get the idea. On the left-hand side, this becomes g inverse of g of x. On the right-hand side, it becomes g inverse of 2. What happens when the g inverse runs into the g? Don't say cancel, they go poof, because cancel is already inverse identity, and there's no such thing going on here. They go poof, and you're left with x. So we've gotten x totally by itself. And then we have it equal to g inverse evaluated at 2. This is just that weird function idea. I can evaluate this. Take 2, plug it into this thing. So this becomes the cube root of 5 minus 2 over 3, better known as the cube root of 1, which is equal to 1. So x is equal to 1. Zero algebra. Isn't that kind of cool? So if you have a function and its inverse, you can use them to offset one another to solve equations. That's the beauty of it. Most people don't like this. But this is the power of math. There's zero algebra going on here. If I'm giving these two functions to begin with, there's not one thing you move to the other side. It was all just plug and play. I find it much easier than going through and actually solving them. Cool things we can do with math. All right, how about
We follow the same steps on the board.
why would you change it? Okay, math. No, just because it looks different, don't do it different. Do it exactly the same. Go ahead, try to start. You'll get stuck eventually. I'll help you on the stick when you get there. I just want to make sure I'm covering everything I need to. Well, at least I hope you got this far. You can combine number 1 and number 2 in one step if you want. It's not that hard. Now what? Solve for y. So how do you solve for y? Back to how do you solve a linear equation for a singular variable? Have we done one like this in chapter 1? Yeah. It looked almost exactly like this. Yeah. So you've seen it before. So how do you solve an equation like this for y? What would be your first step?
Follow the same steps. Just
No. I'm doing that. I'm on solve for y. So how would you solve for y? What?
Multiply y plus 7 on both sides.
Multiply both sides by the common denominator. Never want to solve an equation with fractions in it, get rid of the fraction first. Alright. Now, change colors. This side, if you distribute the x, is going to become xy plus 7x is equal to, these two are going to cancel each other out, and you're just left with 3y minus 1. Okay. Then I go back to my little repetitive step. How do you solve for y? What would you do next? You have all done this before. And you actually were pretty good at it when you were doing it.
I would put the y on the same side.
Put the y's on the same side. Which one do you want to move? Move the xy over? Alright. So that'll bring us to 7x is equal to 3y minus xy minus 1. Notice I try to get the y's next to each other also, rather than putting them on the opposite sides of that 1. Alright, now what? Move the 1. So get the 1 away from the y's, so you get 7x plus 1 is equal to 3y minus xy.
Factor,
Factor what?
like y.
Oh, yeah, they have a common factor, don't they? Y. So you get 7x plus 1 is equal to, kick out the y, what's left behind? 3 minus x. And then,
Divide.
so you're going to get y by itself. You're going to have 7x plus 1 in the numerator, 3 minus x in the denominator. You remember doing this, right? I know it's been a few weeks, but not that many. And then the last step is replace the y with its functional notation. So it would be f inverse of x is equal to 7x plus 1 over 3 minus x. Let's play with this for a second. What if I go through and I actually compose them with each other? I know what the answer is supposed to be. It's supposed to be,
Break time.
huh? It's not supposed to be break time.
7 o'clock.
I don't get break time at 7 o'clock, 7:15. So, what's the answer of this supposed to be? X. It's just x. The x is going to go away, and the x is left over. But I'm going to do it the long way. So the function on the outside is f, and f looks like 3 times something minus 1 over something plus 7. 3 times something minus 1 over something plus 7. That's the original f of x function over here. Alright, what goes on the something? Well, f inverse of x. What's f inverse of x look like?
7x plus 1 over 3x. I mean 3 minus x.
3 minus x. So that goes here. 7x plus 1 over 3 minus x. Right? Ew. How do you simplify that mess? Stare at it long enough and it'll work itself out without you doing a thing. Now, come on. It's a complex fraction. Something to do with the denominator. Don't say conjugate. It don't work unless it's radicals.
Okay.
This is common denominator. What's the common denominator? 3 minus x. So you multiply everybody by 3 minus x. Including the 1 and the 7, by the way. Multiply every single term by 3 minus x, top and bottom. So when you do that, these cancel, and you're left with 3 times 7x plus 1, better known as 21x plus 3. Over here, you're going to get minus 3 plus x over. Oh, cool. 3's cancel. These x minus 3's are going to cancel, and you're left with 7x plus 1 plus 21 minus 7x. Ooh, that's messy, isn't it? Oh, horrible. Nah, it's not that bad. What happens to the 3's? 21x plus x is 22x. Over, what happens to the 7x's? They cancel, and 1 plus 21 is 22. And your final answer is x, which is exactly what I thought it was going to be to begin with. F and F inverse cancel each other out, and they become x and y.
Why did you do all that? Just
I want to show you how to prove that
Okay.
something is an inverse.
Okay.
So one
so
step,
I don't have to do all that crazy mess if it says.
if you figured it out beforehand. But what if I said f of x is this mess and g of x is this other mess? Are they inverses of one another?
Then
The
I'll
only
have
way to prove it is to compose them
to
with
do
one
all
another.
that.
Do I have to do it the other way too? And most people would say
I hope not.
no, but I'm going to say
Yeah.
yes, and there's a reason. Let me show you the reason. That you actually have to compose it both ways to prove that they're inverses. I'll give you one that you think is an inverse already. Let's see if I can get them in the right order. F of x is equal to x squared. G of x is equal to the square root of x. Is g of x equal to the inverse of f? Is it in the inverse of f? And most of you already think it is, which is kind of scary. But you all think they're inverses, right? If you square a number and then you square root it, you're back to the number you started with. They seem like inverses. So let's do the first composition. F of g of x is equal to. What function do I concentrate on? F. F is something squared. What goes on the inside? Square root of x, which is equal to x. Now it gets a little weird. The domain of the inside function is 0 to infinity. So the answer over here is only 0 to infinity. Because you can't square root a negative number.
Right.
So this number has to be positive. So one of the little add-ons here is x has to be greater than equal to 0. It's part of the domain. It's part of the domain. All right, let's do g of f of x. Well, g of f of x is, concentrate on g. G is the square root of something. And f of x is x squared. Now, that's nice because whatever x is, it's going to get squared, it's going to become positive, so I can take its square root. Okay, so what's it equal to? You know what's funny is most people would say x. They would.
Yeah, that's what I said.
But if x is equal to -3, -3 squared is 9, the square root of 9 is 3, but not -3. Because we started with -3 over here. So what forces a negative number to always be positive? What forces any number to be positive? Absolute value. So this one is actually equal to the absolute value of x. So, are they inverse functions? And the answer is no. Unless we restrict them to both be positive. The domains are positive. Then the absolute values can be dropped and you get x and x. Isn't that weird? So, G is not F inverse on a whole domain. But G is F inverse when x is always positive. So it is possible to have an inverse function with what's called a restricted domain. I talked about this earlier. That if we restrict the domain, we can actually find an inverse. Okay. So you're a little more talkative than the beginning of the semester. I mean, the beginning of the semester, you all just sat here. I was like, what am I going to do with this group? Jeez. Graphing an inverse.
We were just so excited to be here.
Uh-huh. That's so sad. I'm always excited to be here. You guys come in.
It's because you love my house.
I love torturing people. It's nothing to do with the math. It could be any topic, but I love torturing people. So let's say, for instance, I have this graph. It's a horrible picture, but it'll work for me. And this is f of x. What I want you to do is graph f inverse. This is another easy test question. And I really mean it. It is really, really easy. First thing you do is you go and find 3 or 4 points on this graph. Make them up if you have to. They don't have to be perfect. just give you an idea of where things fall. So I would look at this point, definitely the y-intercept, maybe another point up here. This one I might just use 3 points. Some others I might use more. Give me a reasonable coordinate for this first point over here to the left.
5, 1, 5, 1.
Negative 5, 1? Okay. Negative 5, 1. This one?
0, 2.
0, 2. This one?
4,
4, 5. 4, 5? Yeah, that would work. 4, 5. If you're going to find the inverse function, what do you do to the domain and range? Flip them. So you take each one of these coordinates and flip it. So if you flip it, negative 5, 1 becomes 1, negative 5, someplace way down here. So that'd be 1, negative 5. 0, 2 becomes 2, 0, which is right about here. And 4, 5 becomes 5, 4, someplace over here. Yeah, close enough. 5, 4. The picture then would look something like that. Now there's several ways of looking at it. You could just say, yeah, I'm going to flip the coordinates, but it's a slightly bit different than just flipping the coordinates. There's one more added little piece. If you take your paper, rotate it 45 degrees counterclockwise, you should be able to draw a line that goes smack dab right between these two graphs, so it looks like it reflects over the line. You know, if you turn your head a little bit this way. And that line that goes right down the middle of these two, right through the origin, is the line y equals x. Why? Because you replace y with x and x with y. You literally just reflect it over this line. So your graph has to look like a reflection over this line, plus all the coordinates have to flip. That's the two pieces that you need to get a perfect inverse graph. Flip all the coordinates and make sure the image looks like it's symmetrical over the line y equals x. That's it. That's all there is to graphing an inverse. One test question, easy, that people screw up horribly. Don't know why. I think images, and I guess it goes back to grade school and say, out of these two letters, which one is symmetrical? Most people pick A, but don't see B being symmetrical. You know, it's funny.
Fold it the other way.
Yeah, because most people go, oh yeah, you can cut an A smack dab down the middle and it copies itself over left to right. But very few people look this way
Yeah.
for B. Same thing goes with this. It's on an angle, so your reflective capabilities are usually vertical, over a vertical line, not over a horizontal line. And this is over a slant line, which makes it even worse. So sometimes it's best just to rotate your paper 45 degrees to the left, counterclockwise. Make sure that line goes smack dab down the middle of your image. All right, so that's the end of, what was that, 2.7? So now 2.8.